Hi there. We're going to have a look today at the topic area of significance and probability, which a lot of people find quite tricky. So I thought it was worth doing a voiceover PowerPoint on this just to make sure that everyone's kind of got as clear idea about this as possible. I know you may well have touched on quite a bit of this with Ms. Shepherd anyway, but it is pretty useful to go over this again just to make sure everyone is completely clear. So it's all about the idea of significance, which is whether you can take the results seriously or not, whether they're meaningful results, and probability, which is to do with how likely something is. The little subheading we've got there says using inferential tests to determine the importance of our findings. Inferential tests are the statistical tests that you've started to look at last year, so sign tests, other things like Mann-Whitney test, t-tests, things like that. Right, and we use those to judge how credible or believable or significant our findings are. So in terms of what you have to know for inferential testing, there is 3 different bullet points there. First one, you've got introductions to statistical testing, which is the sign test. You have to know that and you have to be able to do it. All right, so you have to be able to carry that out. Next one, probability and significance. We're going to kind of run through that today. So you've got statistical tables and critical values, which I think you've done some with MIS recently, and type 1 and type 2 errors, which we'll have a look through today. And then you've got factors affecting the choice of statistical test, including level of measurement, which you looked at last lesson, and experimental design, and when to use the following tests. Again, you've done some of this from MIS, but I'm going to go through it just to make sure that everyone's kind of got a clear picture of stuff. All right. So key thing with this is that people get freaked out by all this. It doesn't require that much mathematical knowledge, to be honest. You don't have to do all the calculations in the exam, but you do have to understand how they work. All right, so you have to think about how they work, and if you understand how the tests work to some degree, and you can practice doing some of them, then it will help you along with your understanding on it. So you will be helped. You've got 2 different types of statistics. You've got descriptive statistics and inferential statistics. So descriptive statistics, as it says in the definition there, they describe different characteristics of data. These are things like measures of central tendency, which are means, modes, medians, and measures of dispersion, which look at how spread out results are. So that's looking at things like range and the standard deviation, each of which you've looked at before. So that's descriptive statistics, which we tend to use quite a lot. They're kind of the more basic end of statistics. However, the branch of statistics that we're looking at really is more focused on inferential statistics. So as it says there, inferential statistics enable researchers to use the samples of data that they've collected to make inferences about the populations from which the samples were drawn. This definition is key here. So an inference is a reasonable conclusion that can be drawn from information presented. So that means that we can infer or conclude that the findings we obtain on the sample that we study are representative of the population from which the sample is taken. This is the really important thing. So if you are testing, if you're carrying out an experiment on a small group of people, then you carry out an inferential test. That means that you can, and the results are significant, that means you can infer that the findings of your experiment are telling you something significant that can be then generalized to the wider population. So it's all about kind of taking the results you found from your experiment and thinking about how you can apply that more generally. So let's go into a bit more detail on probability and significance. The idea behind probability is all about the idea of chance. So when a psychologist carries out an investigation, they want to be sure that results are not due to chance factors. So they want to be completely sure that the IV is causing the changes in the DV rather than some other random thing, right? Rather than some confounding variable or extraneous variable or just the effects of randomness, right? So they want to be sure to an acceptable level that the results are not as a result of things other than the IV. So let's just think about a scenario here. So imagine you're carrying out a test to see if people are able to recognize colors through their fingertips. You conduct the test by selecting a group of 20 participants, blindfold them, and then ask them to feel different colored discs in a random order. Most of the participants do very badly, but there are a few who seem to do exceptionally well. Fantastic. The media. Get hold of the details of your study and ask one of the participants who did particularly well to take part in a live TV demonstration of their skills. Oh, guess what's going to happen next? This time round, the participant performs appallingly. Okay, so the reason why they did so poorly on air was because they had no special skills in the first place. So they were one of the few that did well, but they were not representative of the bulk of the results, right, from that initial experiment. So it'd been a matter of chance that they'd done well in the laboratory experiment. Now, if nearly all of the participants had done very well, then it's less likely the results were due to chance. And this is how statistical tests work. So the bigger proportion of the sample that demonstrate that the findings that you're expecting to see, the less likely it is due to chance. Basically, is kind of the summary of all this. So on the TV program in this scenario, chance was not on their side and they turned out to be as bad as everybody else because they had no special talents. They could not detect colours through their fingertips. Surprise, surprise. So what do we do in relation to hypotheses in relation to all this? So the decision about what to do with a hypothesis is determined by the significance level that the results achieve. So whether they are significant or not. So if we find a significant result, we can reject the null hypothesis, so the hypothesis that there will be no effect of the IV on the DV, and we can retain the experimental hypothesis that states that the IV is going to affect the DV. If the result is not significant, we keep the null hypothesis, so we take the view that, yeah, okay, all right, the IV doesn't actually affect the DV, and we got the hypothesis wrong and we've been disproven, okay? Now, I'll give you an example of this. So, for example, if you find that boys and girls perform differently on short-term memory tests, how do you decide whether the difference is a meaningful difference or, in statistical terms, a significant difference? The difference is judged to be significant by carrying out an inferential test on the data. And if the difference is said to be significant, we can draw a conclusion that there is a meaningful difference between the performance on short-term memory tests between boys and girls. Because it is significant, there can be practical consequences such as policy changes in the ways that boys and girls are educated. That way, you've applied your findings to the greater population. You've inferred that the results are significant to a wider group of people than the people you've been experimenting on. It's kind of the idea of the whole thing. And I don't know why it's doing that. So you've also got this concept of type 1 and type 2 errors. You can never prove a hypothesis right, because if you ever find any single wrong answer, that would disprove your hypothesis. Does that make sense? What you want to do is you want to demonstrate that your hypothesis is nearly always right, is the idea. And that's why we use probabilities in this rather than certainty. Now, when we say our hypothesis is nearly always right, there are different levels of nearly alwaysness, right? So depending on how stringent or demanding you want to be in terms of the levels of accuracy, you can use different statistical tests. So when you carry out your test, you get your findings and they demonstrate whether they are significant or finding or not. And you have to decide whether or not to reject the null hypothesis. So this means whether you are deciding to say, yeah, actually, yeah, there is something kind of like pretty meaningful going on here. Okay, and the type 1 and type 2 errors come in to this process of whether you reject the null hypothesis or not. So type 1 errors are where you reject the null hypothesis when in fact it's true. So it's an optimistic error. Now this is bad news if you make one of these. So if you think about it, what you're doing is you're saying, actually, I think there is something quite significant and meaningful happening here, when in reality there isn't. Right? Now, a scientist would tend to try to be more pessimistic than optimistic, because you don't want to be finding out, you don't want to be publishing pieces of work saying, oh yeah, I found this great thing, and then people turn around and say, well, no, that's not true, is it? All right, science tends to try to be on the rigorous side. So it would try to avoid type 1 errors. The type 2 error is the other way around. So that's where you accept the null hypothesis when in fact it's false. So you have found a meaningful impact to the IV on the DV, but you make the mistake of saying there isn't a meaningful impact to the IV on the DV. So you're being overly pessimistic. Now, scientists would ideally make these errors more than they would type 1 errors. You're better off being pessimistic than optimistic usually, right? And that's kind of the approach that is usually taken. There's always this trade-off between type 1 errors and type 2 errors, okay? And you have to find this acceptable balance. So in terms of what level you are accepting of type 1 and type 2 errors, right? Usually, most psychologists would accept a 5% possible level of error as acceptable, right? And they would write that as P is less than 0.05, okay, as it's written on there. If a result is any higher than this, then it's said that the probability that results were due to chance is too high, therefore the null hypothesis is rejected, okay? So you're thinking about whether you are confident in whether you have made any type. So what do these different significance levels mean? So if you have a significance level of P is less than 0.05, this means the results being due to chance is 5% or less. And this is the maximum level of chance that is seen to be acceptable. So this means in practice that there's a 5% or less chance of making a type 1 error. So you've got less than 5% chance of being too optimistic and claiming that there is an impact to the IV on the DV when in fact there isn't. Some type 2 errors will be made, but what we kind of seem to be as an acceptable level. All right. It also means there's a 95% chance the results were not due to chance factors. If you think about it, that's fairly good. So if the level of significance is obtained, then the null hypothesis is rejected and the experimental hypothesis can be accepted if our results are seen to be significant, you know, with our critical values tables and observed values tables. So the 5% level is normally selected because it's a good balance between type 1 and type 2 errors, as I've mentioned already. All right. So unless you are told otherwise, psychological statistical testing operates at the 5% level. Okay. It might be that you are asked to state that in an exam question. It might be that you are given more than one different significance level, and you have to kind of make a decision about which one you're going to use. All right, go for the 5% one unless you are told otherwise. What do the other ones mean, basically? So if you got P is less than 0.01, this means the probability of the results being due to chance is 1%. it's a more stringent or demanding level of significance. There's a 1% or less chance of making a type 1 error. So you've got 1% or less chance of making a too optimistic error, but the probability of making a type 2 or pessimistic error is higher. So the more stringent you are, okay, the more demanding test, the less likelihood of making a type 1 error, but the increased likelihood of making a type 2 error. So basically, the lower the number, the more scientific you are, because the more demanding you're being and the more stringent you're being in your testing. Alternatively, it means that there's 99% chance or probability the results were not due to chance factors. And if this level is obtained, then the null hypothesis is blah, 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 same as before. Right? You could also get something that looks like this. Significance level of p is less than 0.001. So this means the probability the results were due to chance is 0.1%. Very, very, very stringent or demanding level of significance. There's 0.1% or less chance of making a type 1 error, but a very high chance of making a type 2 error. Also means that 99.9% chance probability that results were not due to that the results were not due to chance, right? So that, if you want to be absolutely damn sure that you have a demonstrable, serious influence of your IV on your DV, you could test to this level. So, for example, if you were testing drugs, all right, and whether they cured cancer or coronavirus, keep it topical, you might want to test to a 0.001 level, because you don't want to be going around giving people drugs that actually don't work, all right, because you've got your testing wrong. So if you're testing the effectiveness of drugs, then it may well be that you test to a much, much more stringent level. But most psychological research isn't done in that format, so therefore we would probably test to a lower stringency level. And then same things as before. All right. Oh yeah. So I've got an example there. So for example, medical trials of new drugs, all right, would tend to be tested at a high level, unless you're Donald Trump, who's getting his doctor to give him all kinds of crazy coronavirus treatments because someone told him they were good. Basically, not good science, people, not good science. So if you want to get less stringent, you could do p is less than 0.10. So that's similar to before. So less stringent levels, 10% chance of making a type 1 error, but a fairly low chance of making a type 2 error. So you're not really being very scientific if you're doing that. All right, so you wouldn't really tend to do that. If you're doing a piece of research in chemistry, it might be that you're testing at the 0.001 level. If you're doing psychology, it might be 0.05 level. If you're testing in, I don't know, geography, it might be at 0.1 level potentially, or 0.05, same as psychology. So basically, if you're testing at the more stringent levels, you would often, as a discipline, be seen to be more scientific because you are more sure of the impact of your IVs on your DVs, basically. So Donald Trump's testing more to that level. Right, a couple of questions for you to do here. So a couple of questions up there. Could you just pause now and have a think about those, jot down some answers, and then I will go through them with you in a sec. So pause now. And welcome back. So a couple of questions here. What is a type 1 error? Type 1 error is the false positives, where you're being optimistic and you're saying the IV has affected the DV when in fact it hasn't. Number 2, a type 2 error is a false negative, where you're being overly pessimistic, right? And you are saying there isn't an effect of the IV on the DV when in fact there is. Number 3, percentage probability of making a type 1 error at the following significance levels. P is less than or equal to 0.01. The answer to that should be less than, well, 1% or less, because it's less than or equal to. P is less than 0.05 is less than 5%, and P is less than 0.10 is less than 10%. Number 4 is a significance level of P equals 0.001 more or less stringent than a significance level of P equals 0.05. It is more stringent, all right? So that means it's more demanding, which means there is less of a chance of making a type 1 error, which is you being overly optimistic that the IV is affecting the DV. Okay, right. A couple more things to have a look through. All this links into affecting your choice of statistical tests. So if you are doing these statistical tests, you have to choose the right ones, basically, and there are rules to follow, all right? And you've come across these a bit already, but it's worthwhile going over these again just to make sure that all this is kind of fitting together in your head. So if you don't choose the right test, then the results and the conclusions you make will not be trustworthy. The significant results that you find will actually not be significant because they will be inaccurate. So statistical tests are applied to the data collected from the sample in order to infer the characteristics of the wider population. So you've got to do them right because it's not a group of people. The two groups of things that you need to consider when you're choosing which statistical test you're going to use are the type of research design. That's things like whether you are doing a correlational study or you're doing repeated measures or independent groups, something like that, and the type of data you're using. This refers to whether you're using nominal data, ordinal data, ratio, interval data, that kind of thing, which we had a look at last time. So the type of research design is an important fact to consider when you are choosing these statistical tests. So if you've conducted an experiment, all right, so if you're doing an experiment where you're checking the impact of the IV on the DV, you are testing the difference between two sets of data. So if you've done an experiment, then you'll have either used repeated measures or matched pairs or independent measures. Okay, so there are tests of difference and there are also tests of correlation. So tests of correlation are where you are looking to see whether one thing happens when the other thing happens. Okay, so there are correlational tests that we look at and there are tests of difference that we look at. Okay, so your first thing to do is to think about whether you are looking at a correlation or whether you're looking at a test of difference. Okay, and then within that you can then decide. So you need to think about the type of data next. So we had a look at this last time. All right, the 4 different levels. So you've got the nominal data, where data is in separate categories, and basically the numbers that you're using aren't really very meaningful. The categories you're using aren't particularly numerically meaningful. So if you've got 3 categories of hair color, brown, blonde and red, all right, the number of people who are in brown, right, so if there's 3 people who've got brown hair, right, all that means is the 3 people who've got brown hair. Okay, if there's 5 people who've got blonde hair, okay, right, if there's 7 people who've got red hair, fine. Okay, but the numbers don't tell us anything more than that. Okay, so if you've got 3, 5 and 7 there, okay, then that's all they're telling us. Ordinal is the next level of complexity of numbers. All right, so ordinal numbers are ones that are in order in some way. So for example, if you order everybody up, order everyone in height level across the classroom, all right, and you say, you're number 1, you're number 2, you're number 3, and you're down to number 20, all right, you're the 20th tallest. Okay, that means that number 1 is taller than number 2, number 2 is taller than number 3, number 3 is taller than number 4. All right, so your numbers start to mean a little bit more. Interval data and ratio data is where the numbers that you're using mean a little bit more again. So interval data is where you are measuring things, right, with standardized intervals. Okay, so that means if you're measuring something on an IQ scale, right, the IQ, the difference between the IQ of 100 and 101 is the same as between 101 and 102. Okay, So if they have equal intervals, standardized intervals, then you've got interval data. Ratio data is basically the same as interval data, except it's a measurement that starts from 0. Okay, so height is a good one of this, because if you're measuring in centimeters, each centimeter is the same size as every other centimeter, right? So it's interval, but it starts from 0 because you can't have a minus height. That's tricky. Okay, so once we've got those, we can decide what we're going to do. All right, so you have to, as I said earlier, you have to decide whether you're using a test of difference and whether you're using a test of correlation. So that's your first thing you look at. Okay, so across the top, you can see those categories. So if you think you've got a test of correlation, right, you've then got 3 options to choose from. If you've got a test of difference, you've then got 6 options to choose from. 6 options. If you've got a test of difference, you then have to subcategorize it and think, right, am I using unrelated data, right, unrelated groups, or related groups? Okay, unrelated is independent groups, related is repeated measures or matched pairs, right, because the groups are related to each other in some way, they're similar to each other in some way. Right, so you can work out what column you are using from doing that. Right, you also, on the left hand side, you can see the type of data that you're using. So if you can identify whether you're using nominal, ordinal or interval data, you can see which row of the table that you're going to be using. Okay, so basically, if you have that information, whether it's a test of difference or a test of correlation, and whether it's unrelated or related within your test of difference, so that's depending on the research design, and then what level of measurement you're using, so whether it's nominal, ordinal or interval ratio data, then you can decide which test you are going to use. Okay, so we got a couple of questions for you to have a look at here. All right, so if you could just pause the PowerPoint here and just spend a few minutes, probably maybe 10 minutes or so, right, having a look through these and writing down your answers. Then once you come back to me and unpause it, then we will have a talk through how it is that you could go about doing these. Okay. Hello, welcome back. Right, okay, so let's have a look at this. Right, so question 21, right, for some reason the question doesn't say what n is, right, I think that's on the previous slide, right, which I didn't copy in, right, so I'll put use n equals 28 in big red letters, so hopefully you saw that. So we need to interpret this table first. Okay, so as it says in the question, psychologists use Spearman's row to see if the correlation between empathy scores and recognition of facial expressions of emotions was significant. The calculated value, so that's the one that they came up with in the experiment, was plus 0.490. State whether this calculated value of RS, which means Spearman's row, is significant. Using table 1 below, explain your answer. So if we have a look at the table, using n equals 28. So we go down the left-hand side, right, and we can see that the third row down, right, the one with 28 in it, is the one we're going to be using. We then have to think about which column we're going to be using. And we're going to be using the significance level of 0.05 because unless you're told otherwise, that's the one you use. Okay. Then down the bottom, so basically we can see that the important value for us is 0.375 because that's the one that where the intersection between 28 and 0.05 lies. Okay. Down the bottom, underneath the table, it says table values are for a two-tailed test. To achieve significance, the calculated value of rho, Spearman's row, must be greater than the table value. Okay, so it has to be greater than the table value. So the table value is 0.375. Our calculated value, we can see back from the question, was 0.490. So therefore, the result from this experiment is significant because the calculated value is higher than the critical value found in the table, basically. Ta-da! Right, we'll have a look at the mark scheme for this in a sec. All right, see how they spell it out. Number 22, it says what is meant by a type 1 error. All right, as we've kind of talked about already, type 1 errors are false positives. That's where you're being overly optimistic. Okay, second part of the question, explain why the psychologist thought that she had not made a type 1 error, right? If you have a look at the findings here, so it's significant at the 0.05 level. However, it's also significant at the 0.01 level. All right, so it's significant at the 5% level of chance, and it's also significant at the 1% level of chance. So because it is seen to be significant at that higher level, so 0.490 is higher than 0.483, which is the test at the 1% level, the chances of it, the likelihood of it being as a result of chance, is pretty poor. All right, so the likelihood of making type 1 error is pretty low, to be honest. All right, so you can test at the 5% level and the 1% level and the 10% level on this table, and it meets the criteria for all of those. So our observed value, calculated value from this experiment, is higher than the value given for n equals 28 for 0.1, which is 0.318, 0.05, which is 0.375, and 0.01, which is 0.483. So it beats all of those, so it wins. All right. In terms of the mark schemes, how it looks, 21 says state whether the calculated value of R is significant, using table 1 below to explain your answer. In terms of getting the marks, you get 1 mark for correctly stating the results significant, okay, and then 2 further marks for explaining it in relation to the table. So 1 mark for explanation that makes an appropriate reference to the table. For example, the calculated value is greater than the table value, and then the second mark for a detailed explanation. For example, the calculated value for n equals 28, right, is significant at the p is less than 0.01 level, as it is greater than the critical value of 0.483. All right, so like that. All right, great. So it's definitely significant. Okay. So it says down the bottom, the result is significant at both the p is less than 0.05 levels and 0.01 levels. So reference to either is acceptable in this circumstance. It's great. So what is meant by type 1 error? All right, you got a definition mark there. Type 1 error is when the results are accepted as significant when in fact they are not. The alternative hypothesis is accepted when it is actually false. And explain why the psychologist thought she had not made a type 1 error. So you have to include things like those bullet points. So the result's significant at p is less than 0.01. P is less than 0.01 is a stringent or demanding level of significance. The more stringent the significance level, the less chance of a type 1 error being made. The likelihood of the psychologist making a type 1 error is less than 1 in 100. All right, all of that, all right, fantastic. Okay, and I'm going to stop talking now. An awful lot of talking today, and hopefully that has cleared a few things up in your head, all right, if they weren't completely clear regarding all this significance, probability and statistical testing type stuff already. Okay, bit of a whiz-bang lesson today to try to talk you through probably the most difficult concepts, right, the ones that people struggle with most. All right, so I'm going to sign off now. Goodbye.